Problem 62, page 709. Here we have a solid insulating sphere, so it's not a metallic, of radius capital R. So we have capital R has a non-uniform charge density. Okay, it's very important, this point. We have a non-uniform charge density rho. It means rho is not constant. In general, if the object has a charge Q and we have a volume charge density, you have to say Q equals to rho times V. Okay? But if rho is not constant, we cannot write the relation like this. We have to, you have to say Q in equals to integral of rho times dv. Okay, you can say Q equals rho times V only in the case if rho is constant and the charge is uniformly distributed inside the object. But if we have if the value of rho is not constant, you have to say, you have to write Q equals integral rho dv. Okay, we continue. Rho is not constant equals to a r square. A is constant and r as value is less than the radius of the sphere. Okay, first of all, we have to show that the magnitude of the electric field outside the sphere equals to this value. B, show that the magnitude of the field inside the sphere equals to this value. And note that the volume element dV, look here, dV is given. We have its value. dV for a spherical shell of radius r and thickness dr is equal to, we have dV equals to 4 pi r square dr. Okay, let me write the given. First of all, here we have Q in equals to integral of rho dV, because rho is not constant, and rho equals to a r square, and we have dV equals to 4 pi r square dr. Okay, and we have a sphere, non-conducting sphere. So for r outside, here we have to calculate E equals to AR5 divided by 5 epsilon 0 r square, and also we have to find the same of the field inside the sphere. Let me draw the sphere. Okay, first of all, I have to find at this point. Let's say we have a point A. You know, to calculate the field, we have to apply Gauss's law. In this case, we choose a Gaussian surface as a sphere. Okay, and this sphere is positively charged. In this case, the field must be out. Here we have E, and dA also has the same direction with E. We have dA. Okay, in general, the flux equals integral of E dA equals to Q n, I can say here, equals to integral of rho dV divided by epsilon. Okay, here we cannot solve directly. We cannot say directly K equal or the field. We cannot consider the object as a point charge. Okay, I advise you to calculate by Gauss's law, because we have to do some calculation to the internal Q. It's not uniform through the object. Uh, E and dA are parallel, we can say, and E is constant, we can say E dA cosine 0. Before, don't forget, you have to write the conditions. You have to say bisymmetric. We select a sphere of radius r as Gaussian surface. E must be parallel to dA, E must be radial, and E constant at any point on the surface. Okay, you have to write the conditions. Okay, we continue. Uh, Equals to integral of rho equals to a r square, and dv equals to 4 pi r square times dr. Okay, divided by epsilon 0. You know E is constant, we can get out its value. We have finally E times A equals to A is constant, okay, 4 pi constant, A 4 pi, inside the integral we have R 4 dr divided by epsilon 0. Okay, in the given, I think we have the value of the limit value of R. Okay, let me see. Look here. When we talk about Qn, Qn is located inside the sphere, not inside, just inside the sphere. Here we don't have Q in this region. Okay, we don't have Q. So we have Qn. When you say Qn, and we have the limit of, okay, the limit of R must be between 0 and R. Okay, its limit, because we don't have q outside. So here the limit of the integral is important to put it between 0 and capital R. Here we don't have q. So R, which is related to the Qn, must be inside the sphere. It cannot be outside. So the limit here is very important because this limit relates to the value of the charge. Where can we find this charge? We can find only in the limit between 0 and capital R. We cannot find, if we have a charge outside, we have to put the limit to cover all the zone where we have a charge. So here the limit between 0 and R. Okay, because the right side of this equation, you know, flux equal integral equals to Qn divided by epsilon. This part relates to Gaussian surface, and this part is related only to Qn. Okay, so the limit will be, the integral will be limited by the presence of Qn. Okay, we continue. Here we have a and a, so we can calculate the integral of r5 dr for dr equal r5 divided by 5 with the limit between 0 and r. Okay, so we get e. We can cancel a and a. Okay, so let me see. Maybe we have no, no, we don't have the same a because this a is the area of Gaussian surface. Let's say we have a of Gaussian surface, and this a is a constant. Okay, we don't have the same a. This one is constant. It's constant. It's not the same. Okay, and here rho equal a is a constant. It's not the area, but this a is the area. You know, the area of Gaussian surface equals to 4 pi r square. Okay, excuse me, the area. Okay, we substitute the value of a, we get e times a equals to a times 4 pi. The integral here, the integral equals to r5 divided by 5 with the limit between 0 and r divided by epsilon. Okay, we have 4 pi, 4 pi. We continue. E times r square equals to, we do the limit, we get r5 divided by 5 epsilon 0. Okay, so E equals to R equals to R5 divided by, we have A here, okay, times A divided by 5 R squared epsilon 0. Okay, we get the right answer here, equals A R5 divided, okay, 5 R squared epsilon 0. Right answer in the case of R greater than capital R. Now we have to solve the second part to calculate the field inside the sphere. Okay, we have to calculate, let's say at the point B here, we have to take Gauss's area, Gauss's surface, and we don't need to repeat the same conditions. Okay, you can say only one time because we have a sphere for the two cases. Here, just we can see we have dA, and also we have the field outside here. We get the flux equals to integral closed integral E dA equals to Qn. Okay, we put the same value. Qn equals to rho. Okay, we calculated this value, but here we have we don't have the same limit of Qn, because here Qn is just inside this part. The limit of the integral will be between 0 and r, small r, not capital R. Okay, so we get here rho equals to a r square times dv for pi r square dr, okay, divided by epsilon 0. You see the angle between them equals, anyway, all the integral of the Gauss's law, the answer will be EA, because the condition to use Gauss's law, we must have the angle between E and dA. We must have E and dA must be parallel. If EDA have the same direction, we can write EDA cosine 0. If EDA are opposite, you put EDA cosine 180. You get finally minus EA. You have only these two conditions, plus EA or minus EA. It depends the value of the charge. If you have E is inward, you have to put the angle equals to 180 between E and dA. So here we can write EA EDA cosine 0. Okay, EA equals to the integral. Don't forget the limit of the charge between 0 and small r, between this point and this point, Qn, inside this one. We get out a constant. This one is constant, okay? It's not the area. A constant times 4 pi times 4 pi integral of r for dr between 0 and small r divided by epsilon. And you know a equals to a of the Gauss's surface, okay? E times 4 pi r square equals to a constant times 4 pi 4 pi integral of r, here we get r 5 divided by 5, okay, epsilon 0. We can cancel 4 pi and we get finally E equals to the constant A. I write in black. Here we have A times, we can cancel R square and R5. We get finally R3 divided by 5 epsilon 0. Okay, we get the same answer. Right. Okay, it's very important here to know that the sphere is a uniform insulating sphere. So we have, you must have a volume charge density. Imagine you have a metallic sphere. In this case, we don't have a charge inside. We have a charge only on the external surface of the object. Okay? If you have a metallic object, you have to say Q equals to sigma A. You cannot write rho times V, sigma A. So sigma times the area of the sphere, you can calculate it. Okay? Thank you.